We want to find the differential equation governing I sub L of t, the current through this 1 Henry inductor, in this circuit for t greater than 0 after this switch has closed to this position. We have two energy storage elements, a 1 Henry inductor and a 2 farad capacitor, so we're going to expect a second order differential equation. Since we're interested in the differential equation for t greater than 0, the first thing I'll do is display the circuit with the switch in the appropriate position. Now I'm going to be interested in currents through inductors and voltages across capacitors, so I'm going to use those as my primary variables. I've already got those defined in this circuit here, so the next thing I want to do is write my voltage current characteristics for the inductor and the capacitor directly on the circuit diagram. So if the current is I sub L of t assumed positive in this direction, the voltage will be L, which is 1 Henry, times dIL by dt. For the capacitor, if this voltage, V sub C, has this polarity, positive terminal here, the voltage current relationship for the capacitor says that this current will be 2 farads times dVc by dt. Now I've got my passive sign convention and my voltage current characteristics for the energy storage elements written on my diagram. I don't have to remember those anymore. I just have to focus on KVL, KCL, and Ohm's law. So if I call this node A, and if I assume that this is my reference, or 0 volts down here, the voltage at node A is the voltage across the capacitor. So this voltage is just V sub C of t, with this being my 0 volt reference. Now, so this is node A, KCL at A says the sum of the currents leaving the node is equal to 0, so V sub C minus 3 over 1 ohm is the current through the 1 ohm resistor, plus the current through the inductor, which is just I sub L, plus the current through the capacitor, which is 2 dVc by dt, plus the current through this leg. If I combine both of these resistances to a single 6 ohm equivalent resistance, then the voltage across those is V sub C, so I have 1 over 6 ohms times V sub C. That sums to 0. Now I can relate the capacitor voltage to the inductor current by doing KVL around this loop. So the voltage across the inductor, 1 times dIL by dt, is equal to V sub C. Now I have two equations and two unknowns. Those completely describe the energy stored in the energy storage elements. So now the problem is to eliminate the undesired variable V sub C to get an equation purely in I sub L. Normally, I'll do that by solving for one of the variables, usually the one I don't want, and then substituting into the other one. So this says V sub C is di dt, so I can plug that in for this expression and this expression here, and I need its derivative, so taking the derivative of both sides of that, dVc by dt is equal to the second derivative of I with respect to time. And that can go in there. So making that substitution, negative 3 over 1 ohm taken to the other side becomes a 3 amps is equal to Vc over 1 plus Vc over 6, which would be 7 over 6 Vc, which is just dIL by dt, plus I sub L, plus 2 times dVc by dt, which is d squared IL by dt squared. And there's my second order differential equation in terms of I sub L. Now I'm going to find initial conditions on the inductor current and the capacitor voltage. Almost invariably when I do that, I'll rely on the fact that neither of those parameters can change instantaneously, so I look at the circuit just before the time of interest, so just before this switch is closed. So this is an open circuit and there's no current through there. Now if this switch has been open for a long time, the inductor will look like a short circuit since the input is constant, and the capacitor will look like an open circuit. So there's no current through the capacitor, and the voltage difference across the inductor is 0 volts. So if this voltage is 0 volts, then this voltage and this voltage are the same. So this current in here is going to be 3 volts minus 0 volts over 1 ohm. Since this current is 0, that will also be the value for I sub L at 0 minus. So I sub L at 0 minus is 3 volts minus 0 volts over 1 ohm, which is just 3 amps. And since that value can't change instantaneously, its initial value I at 0 plus has to be that value as well. The voltage source is not connected to the capacitor during this period of time, so there's no forcing function here. So V sub C at 0 minus is just going to be 0 volts, which is the same as V sub C at 0 plus. So there's my initial voltage across the capacitor. Now let's look at the final conditions. As t goes to infinity, again, this is a constant input. The inductor is going to look like a short circuit, so there will be no voltage across that. The capacitor will look like an open circuit, so there's no current through that. This switch is in this position, and it's been in that position for a long time. So, since there's no voltage difference between here and here, this voltage is 0 volts. So V sub C at infinity is again 0 volts. That's one of my final conditions. And since there's no voltage difference here, then this current is going to be I sub L of infinity. So this is 0 amps going that direction because there's no voltage difference. So I sub L at infinity is 3 volts minus 0 volts again over 1 ohm, which is 3 amps. Now it's a good idea to check our differential equation with these final conditions. So let's go back to the previous slide where we calculated the differential equation. If I look at these various differential equations as t goes to infinity, so for example, this equation here as t goes to infinity, since it's a constant input function, 3 amps, the final value is going to become a constant. The derivatives all go to 0, so I sub L of infinity is equal to 3 amps, which agrees with our previous value, so we're in pretty good shape. We can also, of course, check our individual equations. If I look at this equation, again, since it's a constant input and we're letting t go to infinity, the derivatives go to 0. So V sub C of infinity is equal to 0 volts, which agrees with what we got from the circuit itself. Now, for this equation, as t goes to infinity, we've found that V sub C is 0, so that term's 0. This term's 0. The derivative of 0 with respect to time is 0. So I sub L at infinity is equal to the negative of negative 3 volts. So negative 3 volts over 1 ohm, which is 3 amps, which again gives us some confidence in our result.